Hey everyone, we're going to pick up with units of concentration in our Chapter 9 lecture slides. So we had previously done a Henry's Law problem, and the slide I'm talking about is right after that. Just to give you a heads up, we are going to cover 6 topics today. Okay, so units of concentration will be the first one, but I'm not going to be spending 20 to 30 minutes on any one topic. Okay, we definitely have more problems packed into these slides than I have time to work, so I will work a few examples of each topic, and then I will come back to the ones I skip over before the exam whenever I do a review. Okay, so I've actually introduced this concept back in Chapter 7 when we talked about the equilibrium constant K and plugging in concentrations to the equation for K, so you have seen something very similar to this slide, but we're officially going to get into the details of it and work some problems with these equations. So concentration, what is it? Well, when you're talking about a solution, which is what Chapter 9 is all about, it essentially is an amount of solute per volume of solution, okay? And we have defined these terms, solute and solution. The solute is what is being dissolved into the solution, which contains the solvent. And there's a few different ways we can represent concentration. Not every way is represented on this slide, but this is the 2 ways we'll learn and use, and 2 units of concentration that are used very commonly. So the first one is known as a weight volume percent. We can convey concentration via a percent. So you could have a 20% sodium chloride solution or a 20% glucose solution or something like that. So notice that weight is a unit of mass. Obviously, volume is going to have units like milliliters and liters. And this makes sense when you have a solid dissolved in a liquid. Okay? Remember that solutions can also be solids dissolved in solids or liquids dissolved in liquids. And if that's the case, it might be a volume per volume percent or a weight per weight percent. Okay? So this is a weight volume percent when you have a solid dissolved in a liquid. So the way the units work out here is that we're going to measure the grams of solute and divide that per the milliliters of solution. And then we always multiply it by 100 over here to turn it into a percent. Okay. Remember that the solute will be a lesser amount than the solvent. All right. So that's why it will always be a decimal. And then you multiply it by 100 to get that percent. So I have this picture on the far right of like an IV, and you know, this is something that, especially if you're going into the field of nursing, you're going to run into IVs, and these IVs have, or they might call them drips, things that we're putting into the body to hydrate it. Sodium chloride, saline solution. You might be, I know women who get epidurals in child delivery might get a drip of a powerful drug. Okay, so you have to know concentrations of those things to make sure that the patient or whoever you're working with is getting consistent concentration over time, which is why they're doing it via this IV. But then what that concentration means, okay, so that you know how much of the total drug or solute that they're getting in their body. And then this note down here, nurses work with molarity, which is the next concentration we're going to talk about, specifically dialysis lab work. Okay, so you will run into units of molarity if you're working in a hospital for sure. And this is just one example. So molarity is, you can abbreviate molarity with a capital M, but it is moles of solute per liter of solution. And you guys are familiar with what a mole is, and obviously a liter. So just know that these 2 equations have different units, and let's do some practice problems with these. Well, after I give you the details on how to properly prepare a solution. Hold on, excuse me. Okay, so quick note on how to properly prepare a solution. So I'm going to read this little line under the title. It says, the volume of a solution includes both solvent and solute. Okay, your solute contains a volume. Usually we think of the volume coming just from the solvent, but it's also the solute. So the way, like, we call this right here of this glassware in this picture right here, we call this a volumetric flask. And obviously you see a hand pouring some yellow solute in it. Okay, so step 1, if you're preparing a solution, is add solute, all of your solute, whatever you're going to dissolve. All right, and you can see that this is a 250, you might not be able to see it very well, but it's a 250 milliliter volumetric flask, okay? So it'll hold 250 milliliters of liquid. And the next step after you add your solute, step 2, is to add some, so I'm going to underline this, some solvent. Okay, we don't add all of our solvent. Why? Well, because if we just add all of our solvent before this solute, this yellow powder, has dissolved, we would end up with a solution that was not the right concentration. Our volume would be too large if we added all the solvent, okay? Because we would have the volume of the solute, which is not dissolved, plus the volume of the solvent, and your volume would be too large. So you add some of your solvent, and then you mix it to dissolve the solute. That way the volume is adjusted. Whatever the solute is going to add to your total volume, that's dissolved in there, that's accounted for. And then step 3 is you add the rest of the solvent. Okay, this is very, very important. You can see here that we have some sort of pipette, some fancy volumetric pipette, dropping in, drop by drop, very carefully, the rest of the solvent to get exactly the right volume so that your solution is exactly the right concentration. Okay, so if I were to ask you on the exam, tell me, how do you prepare a solution? I would want you to walk me through these steps. All right, now let's work some problems. This slide right here kind of hits on what I was saying on that first slide, where I was talking about not all solutions are a solid dissolved in a liquid. So what units would we use to express the concentration of a solid solution, meaning a mixture of a solid mixed into another solid? Okay, if we were doing, this would be a weight per weight percent, not a weight per volume percent, and that would be grams of solute over grams of solution times 100. Next question says, what units would I express the concentration of a solution made by dissolving one liquid in another? So you have a liquid solute this time and a liquid solvent. This one would be a volume per volume percent, and you would use milliliters of solute over milliliters of solution. You just see how the units here match whatever your state of matter, or not state of matter, but whether you're dealing with a mass or a volume, okay? And then obviously times 100 again to turn it into a percent. This right here, if you do the problems that I recommend in the back of the textbook, there is a great problem, and I usually always work it in a review before the last exam 4. It's about Listerine. That's mostly what I remember. Listerine is like a mouthwash, right? And it's got alcohol dissolved in it to help clean and sterilize. And so the amount of alcohol dissolved into the Listerine, it gets at that. So anyways, this is the equation you would use to help work that problem of volume per volume percent. All right, now we are going to work a few problems using specifically our weight volume percent equation, and then we'll work a problem with molarity. Okay, so this first question or problem says, what is the concentration in weight volume percent of 15 grams of glucose dissolved in a 100 milliliter solution? So we are searching for the weight volume percent, which is this part, and we're going to plug in grams of glucose. Here, I'll just highlight. We're going to plug in the 15 grams of glucose. That's going to be plugged in right there for grams of solute. And then we're going to plug in 100 milliliters of solution right here and see what we get. So the weight volume percent is going to be equal to 15 grams. This problem is honestly too easy for you guys. And you say times 100. Okay. So some of you are grabbing your calculators right now. You should, at least. You'll want a calculator out for the rest of this video. But 15 divided by 100 times 100, you might notice that these units cancel. And so it just ends up being 15%, right? Now, you might be asking, what happens to the units, a gram and a milliliter? When we convey, that's why it's so important to convey the W or the V or 2 W's or 2 V's or whatever it is, because it's understood, and we only write the percent side, it's understood that this is a gram per milliliter percent, okay? So we don't have to write that because we might say that it is a weight per volume percent. Now, you don't have to write this out because I'll know when I write the question what information you're given. You only have to write percent, but the units do not just disappear. They're still conveyed with this understanding of what kind of percent we're saying it is, okay? But you just write percent. You don't write the G per ml. Okay. Next question. If I dissolve 180 milligrams of heparin, I always usually pause and ask students, who knows what heparin is? I actually worked with it a lot in graduate school in my research, and it's part of the blood clotting cascade. It's a blood thinner, so you might know somebody who is on a blood thinner like heparin. So it works against blood clotting. But if we dissolve 180 milligrams into 15 milliliters aqueous solution, what's the weight volume percent? Now, again, look at your units. One thing you might notice here is we're not starting with units of grams like we did in this other problem. We started with 15 grams of glucose. Here, we're starting with milligrams. And our equation says it's got to be grams of solute per milliliter of solution. So before we just go plug these numbers into the equation and solve for the percent, we first need to convert this to grams. And this should be very easy for you guys. Okay, 180 milligrams. Do you guys remember how many milligrams are in a gram? That's the info you need right now. 10 to the power of 3 or 1,000 milligrams for every 1 gram. So you calculate that. Essentially, you move the decimal place 3 places to the left. So 0.18 grams of, I'm going to put hep for heparin. So that's our mass, and now we have our 15 milliliter solution. Now we can plug everything in and solve for the percent. So you would say the weight volume percent is equal to, I forgot this 0.18 grams of heparin over 15 milliliters of solution times 100. So again, grab your calculator, work this out. 0.18 divided by 15 times 100. You should get 1.2%. So double check me. It's always scary when I do these video recordings because I don't have anybody to double check me. So I hope these answers are all right. Okay, what was I going to say? Oh, last thing. What if I would have given you, like, what if instead of telling you 15 milliliters, what if I told you that you had, like, 1,200, or, sorry, 1.2 liters of aqueous solution, okay? If I would have given you milligrams and liters, just like we converted the milligrams to grams, all you'd have to do is convert that to milliliters before you plug it into your solution. Okay, so again, even if I give you different units than what your equation calls for, convert it always to grams and milliliters. And those conversions should be pretty easy for you guys at this point. All right. Okay, I'm going to do one more problem on this, so I will come back before the exam and work this practice problem, but I'm going to do this one because it is having you solve for grams of solute. It gives you the percent, which is a great practice because I could give you, essentially, I'm going to highlight it. There's 3 variables to this equation. There's the percent variable, there's your milliliters variable, and there's your grams. And I could give you 2 of the 3 parts and have you solve for the third. You're not always going to be solving for the percent. I could give you the percent and have you solve for grams, which we're going to do in this problem, or I could have you solve for, I could give you percent in grams and have you solve for milliliters. All right, so how many grams are needed to make 0.25? Look, we do have liters here, so we're going to have to convert a 0.25 liter solution of a 1.5% weight per volume. See what I mean? They're conveying the weight and volume, so it's an understood gram per ml right there, saline solution. Okay, so we want to go ahead and plug in 1.5% equals grams. This is the part we're looking for, Okay, so I'm going to put a little question mark here. Per milliliter of solution. Okay, and this is our volume, so we need to convert that before we just plug it in. So I'm going to take 0.25 liters, and I'm going to move it down so that I have space. We know for every 1 liter there is 1,000 or 10 to the power of 3 milliliters. So it should be move the decimal 3 places to the right, which is going to give you 250 milliliters. And this is what I'm going to write right over here, 250 milliliters. Now you still have to write in the times 100. That does not go away. It's part of the equation. And I want to solve for grams. So we're going to use principles of algebra and move everything over until we have grams by itself. So I'm multiplying by 100 over here, which means to get rid of 100, I need to divide on both sides. That's my first step. Okay, then 100 will cancel right here. So now I'm going to essentially undo my percent. 1.5 divided by 100. 0.015. Okay. And so now this equals your grams over the 250 milliliters. Now you have 250 milliliters on the bottom. You want to get rid of that, so you have grams by itself, and the only way to do that is by multiplying 250. You can write it over 1 if you want, so times, I don't have a lot of room over here, 250 milliliters on both sides. So now it cancels here and here, and we will do the 0.015 times 250. And you should end up with 3.75%. Oh, whoops, wrong units, grams. Okay, now again, you might be wondering, how do these units work out? And I just want to reiterate, because you're not seeing everything with this percent. This right here, let me scoot this over for just a second. This is a weight volume percent, okay? And we could even write that in, it's just fine, which means it's a gram per milliliter percent. That's what that means. So once we undo the percent, again, it's not very common to write all this in, but it is a gram per milliliter number. So now when I'm multiplying by this 250 milliliters, the milliliters cancel, okay? And that's why we're left with just grams, 3.75 grams of sodium chloride, okay? So we could write that in. All right. There's that problem, and again, I'll come back to this other problem before the exam. I encourage you to try it on your own and see if you understand it and feel good about it. Okay, this one you're solving for milliliters, which is the other part of the equation we haven't yet solved for. All right, let's work a problem on molarity. Okay, moles of solute per liters of solution. So it says, I dissolve 2.335 grams of hydrogen sulfate, H2SO4, in water and dilute it to 50 milliliters. So this is the total volume of the solution. What's the molarity? Okay, this problem has a little bit of converting we have to do before we just plug everything in. We are supposed to plug in moles of solute on top, but we're given grams. Okay, how do I know this is my solute? Because it says I dissolve this thing. I'm dissolving hydrogen sulfate, which means my hydrogen sulfate is the solute. And the solution is going to be the 50 milliliters. We're supposed to plug in solution in units of liters. So a couple things. We need to convert grams to moles, and we need to convert milliliters to liters. And sometimes you'll have to do that. So we're going to need the molar mass of hydrogen sulfate, which for time's sake, I'm just going to look it up. On an exam, if I just give you hydrogen sulfate, you have the periodic table, you could calculate this. I say for time's sake, and then my internet's super slow. Okay, hydrogen sulfate molar mass. So it is 97.0715 grams per mole. Okay. So I'm going to take the 2.335 grams, and I want to cancel grams, so I'm going to plug the 97.0715 grams on bottom, and this is per 1 mole on top. And when we calculate that, we should get 0.024. If you round, it's 241. Okay, now I want to pause and reiterate on a video lecture, which I know some people hate and some people love it. You should be working these problems with me, not just staring at the screen, watching me do them. I hope you have pencil and calculator out. I hope you're working these with me. That is how you're going to be the most prepared, and that's how this lecture is going to be the most beneficial to you. So if you don't have those things, pause this video and go get them. But I would expect and I hope that you're all working these out with me as you watch this. Okay, the next thing we need to do is take our 50 milliliters and convert it to liters. So there's 1,000 milliliters in 1 liter. And when we divide by 1,000, we get 0.05 liters. And now we have the right units, okay? You see how it's moles and liters, which matches our equation up there? So I'm just going to take these and divide. I'm going to do the molarity is going to be equal to 0.0241 moles. And you can write your substance if you want. Hydrogen sulfate over 0.05 liters. We do not multiply by 100 here, like we did for the weight volume percent. So your final molarity should be 0.48. Okay, and this is understood. Molarity is a moles per liter. Okay, it's not that these units go away. It's just that they're they're understood. When you write 0.48 m, then people, once you're around this field enough, know, or I'm just asking you to know now, m means moles per liter, per 1 liter. Okay, that's an understood one. Okay, the number of moles in 1 liter of solution here is 0.48. Okay, so that's what this m means, is moles per liter. So the units don't just go away, they just are summarized with an m. Okay. All right. I think that's going to be all the practice we're going to do with these two equations for now. I will come back and do more, especially before the exam. But now I want to show you, so not a totally new topic, but I want to show you an application for using molarity as a conversion factor to convert between the two units within molarity, moles and liters, volume and moles. So just the way, you guys remember density, okay? I want to talk about density for a second. Density equals mass over volume, right? And so you would calculate the density in gram per milliliter or gram per cubic centimeter. And we practiced a whole lot using density to convert. I know it was on your chapter 1 homework. Using density to convert between grams and milliliters, okay? And the same idea, same concept, we're going to use molarity now to convert between moles and volume, or volume and moles. So this problem says a blood alcohol content of 0.065 molar is enough to induce a coma. And the total blood volume of an adult male is, on average, 5.6 liters. How many grams of alcohol are necessary to reach this concentration, right? And this would be just pure 100% alcohol. Obviously, people aren't just drinking pure 100% alcohol. So to actually make this more applicable or more relevant, you would have to figure out what percentage a certain intake of alcohol, like if you're drinking a particular kind of drink, you'd have to figure out what percentage of alcohol is this drink. And then you'd also have to factor that in, which we're not doing here, but that's okay. So we're going to start with the volume of blood given, which is the 5.6 liters. So this little diagram, this is right out of your textbook, because your textbook is very helpful for working problems out as well. And then we're going to use the molarity to convert from the volume of blood to moles, okay? Ultimately, the question is right here, right? How many grams of alcohol? So we're looking for the mass is what we're trying to find. ETOH is just alcohol. Cannot spell. This is just one way we abbreviate ethanol. Okay, so ethanol is the alcohol in alcoholic drinks. All right, now what are we going to do? So we're going to use molarity. Where's our molarity? Can you see it? Do you remember which number is our molarity? It's the one with an M. So this is our molarity. And I want to write this over to the side on the right side of the screen for a second to remind you 0.065 M means this, 0.065 moles per 1 liter. That's what that means. Okay, that's what the M means. So we're going to actually separate out those units now, moles and liters, because I want to cancel liters and I want to convert to moles. Then I know how to go from moles to mass using the molar mass, which I actually have written for us. It's the 46.07 grams per mole. So first I'm going to plug in for every 1 liter, there is 0.065 moles of ethanol. Okay, you can write that. And now this is step 1, so we just used the molarity to convert. If you look here, liters cancel. So we have converted from liters to moles using molarity. And now I'm going to plug in the molar mass to convert from moles to grams. All right, so I'm going to plug in for every 1 mole, there's 46.07 grams of ethanol, which is the alcohol. And now we just multiply all this out. 5.6 times 0.065 times 46.07. Hopefully I did that right. 16.77 grams. Let me make sure. Double checking all my numbers. Okay, it looks right. Of ethanol. Okay. Now usually, so ethanol is a liquid, and usually it would probably actually be more useful to know this as a volume. So you could take the density and convert that to milliliters to see how many milliliters of straight ethanol could induce a coma. That's a very bad thing, so we want to stay away from that amount. Okay, that's that problem. So definitely on the exam, you will have to use molarity to convert. We're going to take it a step further and say what happens when we have a chemical reaction going on and we want to look at this chemical reaction. We can use molarity to obtain some useful information if we are also using mole ratio and things like that. So I have this diagram, and it says for the balanced equation in green up here, the lowercase letters are your coefficients, capital letters would be your reactants and products. Okay, so A and B making C and D. And for any balanced chemical reaction that involves where maybe your reactants are not solids, maybe they're two solutions. Okay, so maybe we have a mixture. This is most applicable for a situation where we have a mixture of solutions. Okay, and the things that are reacting, A and B, are in solution form. Okay, and if we know the molarity of these solutions, which we should if we made them and are mixing them, then we can calculate how much product we would get or what the concentration of our product would be. Okay, you've actually seen a diagram like this before back in chapter 6, except for we did it with molar mass. So in chapter 6, you had a diagram. I'm going to write it out real quick. It was like if you have the mass of A, you can convert to moles of A, then you can convert to moles of B, and then you can convert to the mass of substance B. And we had a whole lab, our mole conversions lab, where we would practice plugging in the molar mass for a given chemical reaction. That would be step 1. I remember I called it the 3-part problem. Step 2 would be plugging in the mole ratio. And then step 3 would be plugging in the molar mass again of your other substance. Okay, this is the same thing. This diagram is the same thing, except for instead of molar mass, we're using molarity. Okay, look, the second step is actually identical to the second step in the other diagram, plugging in the mole ratio. And then instead of a molar mass, again, we're just using a molarity, okay? So I'm going to erase this diagram on the right because I don't want anybody to be confused what we're talking about and what we're using this time around. I just want to remind you, you've seen this concept before, so hopefully it's not too complicated. We're really not doing anything new except for using molarity instead of molar masses. Okay, so if we have the volume of a given solution, substance A, we can use the molarity to convert to moles of substance A. Then we use the coefficients in the balanced equation to find the mole ratio, and we use that to convert from moles of A to moles of B. And then we can use the molarity of substance B to figure out what volume of solution B maybe we want to react with a particular volume of solution A. All right. I have 2 practice problems on this. The first one, this one right here, is actually not a perfect fit for this model because it has you, or this diagram, it has you start with milligrams of this magnesium hydroxide tablet, which is not a volume. And I want to exactly follow this diagram since I just introduced it. So I'll come back and work this problem, or I think it's a great problem to try to work. I think you have the tools to work it now. But I want to work this second problem. So find this slide, and it says molarity and stoichiometry. Stoichiometry is just a fancy word for using a chemical reaction to calculate or convert and find useful information, essentially is what that is. All right, hopefully you found the slide. So calcium carbonate, let's read the problem, reacts with hydrogen chloride, which is hydrochloric acid, to make calcium chloride, water, and carbon dioxide. How many milliliters, so this is what we're trying to find. How many milliliters of a 0.22 m, and I will read that as 0.22 molar, okay, solution of calcium carbonate are needed to react completely with 25 milliliters of a 0.5 molar solution of hydrochloric acid. All right, so we have a solution of calcium carbonate, we have a solution of hydrochloric acid, they're going to react. We know the volume of our hydrochloric acid solution, but we want to say how many milliliters of our other solution do we need to get the right reaction. So the first thing, if I give you a problem like this, step 1 is write a balanced reaction. Okay, so calcium carbonate, calcium and then carbonate is CO3. Calcium is a +2 cation, carbonate is a -2 anion, so we just need one H, CaCO3. Then it says reacts with hydrogen chloride, which is just HCl, hydrochloric acid. To make, so now here are my products. I have 3 products I need to write. So I'm going to draw my arrow. Calcium chloride. Calcium is a +2. Anybody remember what chloride is? As though you guys can tell me. -1. So I'm going to need 1 cation, and I'm going to need 2 chlorides. So it should be CaCl2 plus water. You guys know water, H2O, plus carbon dioxide, CO2. It does not tell me to include the states of matter here, so that part is not important right now. But these are going to react, and we need to balance it, don't we? So I have 1 calcium on both sides. I'm going to need 2 H and 2 Cl on the reactant side. Is it now balanced? 1 carbon, 3 oxygens, and collectively, I think we're good. I think that's it. So here's the balanced reaction. How many milliliters of a 0.22 molar solution of calcium carbonate are needed to react completely with 25 milliliters of a 0.5 molar solution of hydrochloric acid? Okay, so rereading that question part, we have to go back to our diagram. We have to start with a volume, okay? And it says right here that the volume, start with whatever volume you're given. Now, it says start with the volume of solution A, okay? The only reason it's saying A here is because it's trying to get you to think about this generic reaction up here. We don't have any A's or B's or C's or D's. in our equation, we have actual molecular formulas. So I want you to find the one volume that you're given and write that down. That's what you're going to start with. So if you're looking through the problem, the only place I see a volume is right here, 25 milliliters. So we're going to start with that, 25 milliliters of what? This is hydrochloric acid that we're talking about. Okay, so I'm going to write that in, HCl. I encourage you to write your substance in, label things with what substance you're talking about. And now, what is the first step we do? So we want to use the molarity to convert to moles, okay? Now remember, molarity is moles per liter, okay? The volume unit there is liter. We are not starting with liters, are we? We are starting with milliliters. So there's actually a pre-step here where we need to convert milliliters to liters, and then we can use that to cancel liters and convert to moles. Okay, so we're starting with milliliters, so this is the first step we need to do, is convert to liters, and then we can plug in our molarity. So I'm going to come back down here and quickly convert this to liters. So there's 1,000 or 10 to the power 3 milliliters in 1 liter, and now milliliters cancel. And if we calculated this, we would have liters, which we don't have to. We can just keep going. So now, this is my step 1 in my 3-part problem. Okay? Technically, the first step was converting milliliters to liters. But if we're actually following the diagram that I keep scrolling back up to, this is step 1. We're going to plug in the molarity. Okay? So what is the molarity of HCl? Go find that in your problem. It says 25 milliliters of 0.5 molar solution HCl. So it's 0.5 molar. And remember, this 0.5 molar, well, is moles per liter. It's 0.5 moles per every 1 liter. That's what the capital M stands for. So I'm going to separate out those units or write them all in. And I want to cancel a liter, so for every 1 liter there is 0.5 moles HCl. Okay? So liters will cancel. And now I just have moles of HCl. So this was step 1, plugging in the molarity of HCl. So now we're going to go to step 2. Step 2 in these diagrams is always plugging in the mole ratio. And what are we trying to convert between? The question, which starts right here, how many milliliters of a 0.22 molar solution calcium carbonate? So we're trying to find volume of calcium carbonate. We're starting with volume of HCl. So the two things I'm looking at are right here. I want to get the mole ratio between calcium carbonate and HCl. And if you're looking at the coefficients, that is a 2-to-1 ratio, right? So I have, if you notice right here, I have moles of HCl on top. So I want to cancel moles of HCl. So I want to put the moles of HCl part on bottom in my mole ratio. And I want to put moles of calcium carbonate on top so that we cancel the right thing. And that is a 2-to-1 ratio. So I'm going to plug in my mole ratio there. So moles of HCl cancel. That was step 2. Step 3, if we go back to the diagram, what was step 3? So this is step 1, this is step 2, this is step 3. Okay, now we did have this pre-step, which I numbered 1, but on the actual diagram, 3-part problem, we plugged in molarity, mole ratio. Step 3 is right here. Use molarity as a conversion. Molarity of what? Molarity of your next substance. They're calling it substance B in this diagram because of our equation at the top. But what would be the next substance? What are we trying to find? It would be, we're going from HCl to calcium carbonate. That's what we want to know, how many milliliters of calcium carbonate. So I'm going to plug in the molarity of CaCO3. Do we have that? Can you find that number in the problem? It's the one number we haven't used yet, which is this right here. 0.22 molar, which is 0.22 moles per liter. Remember, this is 0.22 moles per 1 liter. That's what capital M stands for. So this time I want to cancel moles and I want to convert to volume because I'm trying to find out how many milliliters. So for every 0.22 moles, that's how many moles of calcium carbonate are in 1 liter for this solution. And now we see that moles of calcium carbonate cancel. And now we just have liters. So if we stopped here, we would know how many liters of this 0.22 molar solution we would need. The question says how many milliliters. So we got to go one more step. This is not actually on the diagram. But if it asks you for milliliters, you always have to go back at the end and convert back to milliliters. It seems redundant because here we converted from milliliters to liters for HCl. We're not talking about HCl anymore, okay? So we have to now take our liters of the calcium carbonate solution and convert back to milliliters if the question says how many milliliters. So for every 1 liter, there's 1,000 or 10 to the power of 3 milliliters. And once we get our answer now, it'll have the proper units, milliliters. Okay, this was a 1, 2, 3, 4, like 5 steps total. So we're going to do 25 divided by 1,000, or 10 to the power of 3, times 0.5 divided by 2 divided by 0.22, or you can always say times 1 over 2 or times 1 over 0.22, and then times 1,000. And when I did that, I got 28.41 milliliters. So I'm going to have 25 milliliters of my hydrochloric acid solution, and I need 28.41 milliliters of calcium carbonate to react with that at these particular concentrations. All right, this is where I wish I could say any questions, but please write your questions down. If you do have questions on this, like why did she divide by 1,000 or multiply by 1,000 here, or how did she know what to plug in here, please write those questions down, and I would love to answer those if you email me or plan to come meet with me on office hours this week. All right, so I told you we're covering like 6 different topics. That gets us to our next topic, I think our third topic here, dilutions. Okay, with solutions, you sometimes have to dilute things or make things more concentrated, and there are ways to do that. Particularly talking about diluting stuff, I'm going to just read this first statement on the slide. It says, we're often given a solution that is more concentrated than we need. This is usually called a stock solution. So we must add more solvent to dilute the solution to the concentration that we need. And the one we're going to need, the one we're working with, is called our working solution. So when you're doing something like this, I know for our university, here in the chemistry department, when you guys show up for lab, everything's already been measured out in the right concentrations in these nice little clear dropper bottles that you often see on the benchtop when you show up to lab. But there are people who work up in what we call our stock room who take our stock solutions. We order things in bulk, since we run a lot of labs in this department. We order things in bulk, and then we have students that are paid by our department to make the right concentration for the labs that students work in and need, and the concentrations in y'all's lab procedure. So the bulk solutions we order are called our stock solutions, and these kinds of things happen all the time when we're making solutions for our labs. So how do we know how much solvent to add to get the right concentration that we need for our working solution? We have an equation for this. It's probably going to remind you of a gas law. Anybody, does this remind you of P1V1 equals P2V2? Boyle's law. It looks very similar, right? Except for it's M1V1 equals M2V2, where M is the molar concentration. It's concentration in units of molarity. V being the volume. And it doesn't matter if the volume is in milliliters or in liters, as long as your V1 and your V2 match. Okay, so V1 and V2 need to match units. Okay. If you have one that's milliliters and one that's liters, you will get the wrong answer. So anyways, you know how to use Boyle's law, this one right here. And we're going to use the dilution law here. It doesn't have a particular name, the same way. Okay, so we're going to work a problem with this where we're going to be given 3 of these 4 variables and we'll be looking for the 4th. All right, so let's work these 2 problems, and this dilution is rather a pretty quick topic. So it says I have 75 milliliters of 3.5 molar glucose. I dilute it to 450 milliliters. What is the new concentration? So go through and label. This is the first volume given, so that's V1. This is the first concentration given, almost wrote C. So this is M1. I'm going to dilute it to my new volume, which is V2. And so what is the new concentration? I'm looking for M2. Now, notice units of volume are both milliliters, so we're good here. We don't have to convert anything. We can just plug it all in and solve for M2. So 75 milliliters times the 3.5 molar, and you do not have to write out moles per liter. You can just plug in M. Is going to be equal to M2, because that's what I'm looking for, so I don't know what that is yet. So I'm just going to write M2 times 450 milliliters. So to solve for M2, I need to move the 450 over, so I'm going to divide both sides by 450. It cancels over here. All of it cancels. And now we just do the math. 75 times 3.5 divided by 450. And you should get 0.58, repeating 3. And the unit there is molarity. Okay, so that is M2. That would be the concentration, the new concentration. All right, one more dilution problem. It says I can buy 1 molar NaOH. I need, so if what you can buy, this is probably your stock concentration. So this is going to be M1. I need 750 milliliters of my new concentration, this is M2, of NaOH. How do I prepare this? Okay, this is the first volume listed in the problem, but it's tricky here because this volume is for M2. I need 750 milliliters of this new concentration. So this is actually V2. That volume goes with that concentration. So when it's saying how to prepare this, essentially what I want you to do is figure out what volume. I would probably word this differently on an exam. I'd probably say what volume of your stock concentration do you need? And then you dilute it to 750 milliliters with like water or something. So we're looking for V1 is what I'm trying to help you understand here. Maybe you already understood that. All right, so now if we're looking for V1, we know M1, which is 1 molar, times V1 is going to be equal to 0.32 molar times 750 milliliters. Okay. We don't have to convert milliliters to liters here. It's fine to work this with milliliters. We just have to understand that units on our answer are going to also be in milliliters, since that's the starting unit for volume. All right, so to solve for V1, I'm going to divide both sides by 1. Cancels. So we'll just do 0.32 times 750. Obviously divided by 1. It's not going to change the number. So that is going to be our volume of this 1 molar NaOH. We're going to need 240 milliliters of it. And if I were to ask you, remember that slide where I showed you the flask with the yellow powder and we talked through the steps of how to prepare a solution? You could then talk me through, okay, well, actually that's probably not a good example because that was dissolving a solid in a liquid. Okay, forget what I just said. You just tell me, I take 240 milliliters of my stock solution and I dilute it to 750 milliliters with water or something like that. Okay, so that was V1. All right, that's the next big topic in Chapter 9, dilution. So that was kind of quick. This equation's not very complicated. We've seen something like this before. When we worked Boyle's law. And so I'll work more dilution problems before the exam. There's also lots of good textbook problems for you guys to practice with dilution stuff. But I'm going to move on to the next topic. I think we only have 2 topics left, electrolytes and osmosis. Okay, so electrolytes. You guys have heard this term before. When you buy like a sports drink or something, you talk about the electrolytes in your sports drink. So it says ions dissolved in solution are called electrolytes because the solution can conduct electricity. Once ionic compounds are dissolved or disassociated is what I'm going to write. I think there's 2 S's there. Disassociated, we talk about the ions, not the compounds. Okay, and this is especially true for blood because our blood contains lots of ionic compounds in it, or lots of ions, such as sodium and chloride and potassium and magnesium and calcium. And so I just want to prove this point to you that when we're talking about electrolytes, sorry if you can hear all that noise. My office is down by all the instruments. Look at this picture I have down at the bottom. I have like 2 beakers of water. And what if we added 2 different substances, sodium chloride and potassium bromide? And then what if we added potassium bromide and sodium bromide and potassium chloride? These are 2 different substances. But once we put them all in solution, they disassociate. So you end up with sodium. I don't know if you can see red very well. You end up with sodium. You end up with potassium. It's all disassociated. You end up with sodium and chloride. And then you also end up with potassium and bromide. So you got these arrangement of ions. These are the only ions present, no matter how much of the stuff you dissolve. And then in the other one, sodium bromide, once it disassociates, you end up with sodium, and you end up with, I keep wanting to say potassium, bromide. And then you also end up with potassium, and you end up with chloride. Now look at the beakers. If you notice, once everything's dissociated in ion form, the solutions are exactly the same. So this is emphasizing the point that as electrolytes, we could dissolve 2 different substances but end up with the same ions in solution, because when we're talking about electrolytes, we're just acknowledging the ions, not the compounds that they came from. Okay, the next thing to know about electrolytes is that there are different there's different strengths to electrolytes. We have strong, weak, and substances that we call non-electrolytes. This is in section 9.8 of your textbook. I encourage you to go read it. This figure, I know it's kind of grainy, is right from your textbook. And so I want to walk you through what is a strong electrolyte. Okay, so sodium chloride is a solid. It's an ionic solid. When we put it in water, it completely dissolves, right? Which is what it says, dissolves in water. I want you to notice this arrow is a one-way arrow. We don't have a reversible arrow, which means this reaction happens one way. Okay, we're not going to get the reverse reaction. We're not going to get these ions coming back together to form sodium chloride. So when you have a one-directional arrow, one arrow, that means complete ionization, okay? Which is what I want to highlight here. Complete, I probably should use this color. Completely ionized. That is a strong electrolyte. Something that completely ionizes is a strong electrolyte. So you get all ions as your product, okay? All sodium and chloride ions. Okay, a weak electrolyte is a little bit different. Here we have acetic acid. And this is a weak acid. We haven't discussed acids and bases yet. That's chapter 10. But it's a weak acid, and it says dissolves in water, but what do you notice? This is going to reach an equilibrium. We've got a reversible arrow, which means we have the forward reaction into ions, and we're also going to get the reverse reaction where these things come together and remake acetic acid. So at equilibrium, you're going to have some acetic acid, and you're going to have some ions, okay, which is what I'm going to write, some ions, okay, and that happens specifically when you have this double arrow, indicating you have some sort of equilibrium between your reactants and products. That's a weak electrolyte. A non-electrolyte would be like this reaction right here. So we've got glucose. Glucose is not an ionic compound, okay? It will not dissociate in any form. You might have a bunch of molecules of glucose packed together, okay? Think about like a sugar cube. And when you put that sugar cube in some hot water or like hot tea or something, they might dissolve, but they don't dissolve into ions, okay? They just dissolve into individual glucose molecules, okay? So we get no ions, okay? Obviously, ions have charges. You guys know that. We have no charge when glucose dissolves. It does not, a glucose molecule itself does not break up into ions, okay? And then two, double arrow here indicating that you have some sort of equilibrium between our aqueous glucose and our solid glucose. So I had this awesome QR code. I was going to show you guys these three. You know what? I actually think I still want you to scan this and put your answers in so that I could talk about it the next time we meet for lecture. Or just see how well you guys understand what I just said. Yeah, so instead of me walking you through this, pause the video, scan the QR code, do this problem. I want to know this H3PO4, insulin, and HCl, which one is a strong electrolyte, a weak electrolyte, or a non-electrolyte, okay? Yeah, go ahead and do that. All right, hopefully you did. And hopefully, I'm trying to decide if I want to go over the answers right now or not. Yeah, I probably will. Okay. So if you notice on number 1 here, we have a double arrow. We're going to reach an equilibrium, but we do have ions. Oh, I forgot to write this in. This was a negative. Okay, we do have ions on the product side. So some of y'all may be confused that I had no charge on the anion. So we're going to get some ions, okay, which matches this weak electrolyte here. So this will partly ionize. So this is a weak electrolyte. All right, insulin is a solid. It's a biological molecule similar to glucose, and it will dissolve in water, but on the product side, we get no ions. Okay, so this must be a non-electrolyte. And then number 3, we have HCl, a one-directional arrow, and we get all ions. This completely disassociates, completely dissolves for our products. No equilibrium here, so this must be a strong electrolyte. Okay. Notice that a lot of the biological molecules like insulin, glucose, fructose, sucrose, things like that are going to be non-electrolytes. Okay. All right, that's electrolytes. Now, considering we were just talking about ions and charge, kind of connected to that idea is this term equivalence, which we abbreviate capital E lowercase q. So do not confuse this with equilibrium. Equilibrium is usually capital EQ. Equivalence, same letters here, but capital E lowercase q, equivalence. So what is an equivalence? When we have a solution, sometimes we can talk about it in terms of equivalence instead of terms of like molarity or percent. So an equivalent is the number of ions that carry 1 mole of charge. 1 mole of charge. And I'm going to unpack that in just a minute. Okay, so just hang with me, even if you're like, I don't know what a mole of charge is. So why are equivalents important? And then I'm going to unpack what a mole of charge is. Well, our blood contains, or I should say maintains, a certain concentration of charge. Okay, our blood has lots of electrolytes in it, and it's important that the charge balance, like the amount of positive charge from the positive, the cations, and the amount of negative charge from the anions in our blood are maintained. And I actually have a table right here to show you what those concentrations are of positive and negative charge, okay? I'll come back to that in a second. Anybody ever heard of hydration therapy? Okay, so this is another reason why equivalents are important. Let's say that you get really sick and you threw up all night long and your body is depleted, okay, especially for children who have small bodies. What might I then give my son or daughter if that's the case and their body is dehydrated, okay? A lot of people in third world countries that get diseases from drinking infected water or bad water, they have a lot of diarrhea and their body is in a constant state of dehydration. And hydration therapy is what they can use to balance out the electrolytes in the body. Okay, so you ever heard of Pedialyte? I bet you have. They even have it for adults. If you look on a bottle of Pedialyte, or if you Google the nutrition label for Pedialyte, it will measure out the concentrations of the ions in equivalents. Okay, you'll see this on the nutrition label. Okay, because this is how we talk about charge within these solutions, so that as we're hydrating the body, as we're putting these things back into our body and back into our blood, we're just understanding that all of these ions and electrolytes have a certain amount of charge, and we're focusing on the charge. Okay, what is a mole of charge? What is an equivalent? Okay, well, an equivalent is 1 mole of charge, and we know ions have charge. Okay, so if I were to ask you, 1 mole of sodium cations, how many equivalents is this? Okay, all you're going to do is take the number from the mole, multiply it by the number on the charge. Obviously, there's an understood 1 here, and that's how many equivalents you have. So if I have 1 mole of plus 1 charge, then I have 1 equivalent. Okay, so all I did is I did the 1 times 1, and I said, okay, I've got 1 equivalent. That is 1 mole of plus 1 charge. Now, it could also be negative charge. It doesn't have to just be positive charge, okay? And we'll get to that on a practice problem in a minute. What if I have 1 mole of calcium ions, which each calcium ion has a plus 2 charge? So I'll take the 1, and I'll say times positive 2, which means I have 2 moles of charge, right? So I've got 2 equivalents. I'm taking the number of moles and I'm multiplying it by the number in my charge on my ion to get the number of equivalents. Okay, what if I have half a mole of calcium ions? Well, then I'll take 0.5 moles. I'll say times 2, which means I have 1 mole of charge. So I have 1 equivalent. All right? Hopefully that's not some terrible math. Hopefully that's pretty easy. But it is sometimes an uncomfortable idea for students to talk about a mole of charge. But I want to summarize right here. You may notice 1 mole of sodium ions has the same quantity of charge as half a mole of calcium. Why? Because the charge is double on calcium. So you only need half as much of it to give you the same number of equivalents. All right. There's also such a thing as a milli-equivalent, which is abbreviated as MEQ. And these are used frequently because low concentrations of ions in the blood. Okay, so that's what this table shows you down here. Some of them, like it probably doesn't surprise you that sodium and chloride are present in the blood in larger amounts. We need sodium and chloride for lots of things. But then a lot of these other ions are present in lesser amounts. And these are all measured in milliequivalents per liter. Okay. I'm not going to ask you to memorize any of these numbers off this table. I'm just using it as an example to show you some things. Okay. All right, I want to work another problem or two on equivalence, and then we're going to get to our very last topic, which is osmosis. We're going to have to skip a few slides to get there. Okay, how many equivalents of aluminum cations are obtained from 1 mole of plus 3 cations? So again, you're going to say I've got 1 mole, and I'm going to say times, I've got a positive 3, so I've got 3 equivalents. Okay, now if I ask you, all right, I only need 1 equivalent. That's why I'm changing the question here. If I said I only need 1 equivalent, how many moles of aluminum plus 3 cations would give me 1 equivalent? You say, okay, well, I know 1 mole gives me 3 equivalents, so I just want 1/3 of that, right? So I would just take 1 mole and divide by 3, and I'd say, okay, 0.33 moles of aluminum plus 3 cations would give me 1 equivalent. Does that make sense? I hope so. Again, if you're like, no, that doesn't make sense, write that question down, email it to me, come see me, catch me after class on Thursday. Please, I want to know your questions from this lecture. Okay, now I told you it doesn't have to just be positive charge. So far, we've just been talking about all these cations. Well, we can also talk about anions because anions have a charge. And it doesn't say an equivalent is 1 mole of positive charge. It just says an equivalent is 1 mole of charge. So that charge could also be negative. So how many equivalents of fluorine anions are obtained from 1 mole of fluorine? Okay, so you do 1 mole, again, times the charge, times -1, and that is 1 equivalent. That is 1 mole of charge. Where it can get complicated is if I say, okay, what if I have aluminum fluoride, AlF3? How many equivalents do you have? If I have 1 mole of aluminum fluoride, how many equivalents is that? Well, you've already looked at 1 mole of aluminum cations is 3 equivalents, and 1 mole of fluoride anions is 1 equivalent, but we don't have the exact same numbers. If I have 1 mole of this substance now, I have, when that disassociates, I have 1 mole of aluminum plus 3 cations. How many moles of fluoride anions am I going to have? For every 1 aluminum cation, I need 3 fluoride anions. So if I have a whole mole of aluminum cations, I need 3 whole moles of fluoride anions. Okay? Now from here, I think you can get it. You would do 1 times the charge. That's a weird 3. Okay? And that would be 3 equivalents just from your cations. And then you do 3 times the -1, which is going to be not -3 equivalents. Really, you're just looking at the number here, which would be 3 more equivalents. So total, I would have 6, 3, and another 3 for my anions, 6 equivalents. Okay. Again, we're not saying these are negative equivalents. That doesn't make sense. An equivalent is just a mole of charge. Okay, and a negative charge is still charge. So 6 equivalents total. Okay. So if I give you what am I trying to say? A compound. You just break it up into its cations, and then you calculate the equivalents from that. All right, we are going to skip over properties of colligative properties, elevated boiling point, freezing point depressions, and we're going to go straight to osmosis. This is our last topic, and then we'll be done. I'm probably going over time, I bet. All right, osmosis. So I bet when you were in high school, this is what everybody joked osmosis was, right? Some of you probably tried it. It would actually be really awesome if this is how information was disseminated. If we could just sleep on our textbooks and learn. Get the information into our brains that way. But that's not how it works. So, osmosis is the passage of, let's define it, solvent, okay, through a semi-permeable membrane separating 2 solutions of different concentrations. That's a lot of big words. What does this mean? So first off, you know what solvent is, right? Because a lot of people get this part confused. They think it's the passage of the solute particles moving. It's kind of weird to think about the particles staying still and the solvent moving. Okay, but that's what osmosis is. It's the passage of solvent through a semi-permeable membrane. What is semi-permeable? Okay, look down here. If you have this picture, this black line right here would be it's dividing 2 sides of my solution, the solution on the left from the solution on the right. And a membrane, think about like a cell. Every cell has a membrane, right? And some things can pass through it and some things can't. And that's what it means when it says semi-permeable. Usually small things can pass through just fine with no help. A lot of the bigger things like proteins or things passing into and out of a cell have to have help, all right? So the things that don't need any help and that can pass right on through are permeable. And so when the membrane is selectively permeable, we say it's a semi-permeable membrane. All right, separating two solutions of different concentration, okay? And the last thing I want to say before I define and fill in these other blanks is that the solvent, make a note of this, always moves from low concentration well, you know what? I'm gonna make this a little more specific. The solvent moves from an area of low solute concentration. I'm gonna abbreviate the word concentration to an area of high solute concentration. Okay? It always moves from an area of low solute concentration towards or to an area of high solute concentration. That's the way the solvent moves. This right here is what we call a gradient. Okay? When you have a separation of concentration, you have a gradient. And you probably have even heard that in some of your biology classes before. So if you're looking at these pictures down here, this would be my area of low solute concentration. This would obviously be the area of high. The red dots, represent your solute. Okay, so we got low solute concentration on the right, high solute concentration on the left. All right. Now I want to come back up here to these blanks. Osmosis depends on the concentration of particles. We don't care about what the particle is. We just care our particle identity. We just care about how many particles there are. Okay? We think of all particles the same. So osmolarity, how do we define it? If you were to calculate osmolarity, because you can calculate osmolarity, it is the moles of particles divided by liters of solution. Okay, very much like just molarity, right, which is moles of solute per liter solution. But osmolarity is in particular moles of particles. Now, how the heck do we define a particle? What is a particle? It's actually really simple. Look at a substance like sodium chloride. If you have a substance that will dissociate, you're just going to count the number of particles it would dissociate into. This would dissociate into one sodium cation, and it will dissociate into one chloride anion. That is two particles. One particle, two particles. Okay, so if you have 1 molar sodium chloride, you just multiply the number of particles times your molarity to get your osmolarity. I'll show you that again, but you always figure out how many particles am I going to get from my compound, and if it helps, write those out, and then you count those number of particles and you multiply that by your molarity to get your osmolarity. Okay, what about glucose? If I have 1 molar glucose, we've already talked about the fact that glucose will not dissociate. It won't break down any further. It won't break apart into ions. So glucose is your particle. So that's why we're saying here 1 molar times 1 particle is just 1 osmol. All right. So some compounds like glucose, insulin, fructose, sucrose, these non-electrolytes, they're not going to give you particles, any more particles. They themselves are the particles, so their molarity is equal to their osmolarity. All right, so I want you to look at, again, these two solutions I have that are separated by this semi-permeable membrane. And on the right side, it says the concentration of particles is 1 osmol. On the left side, it says the concentration of particles is 3 osmol. I want to define 2 quick words here. Whenever you have a lower osmolarity, a solution with a lower osmolarity, we call this hypotonic. Hypotonic. Whenever you have a solution with a higher osmolarity, we call it, you probably can guess, hypertonic. Okay. Okay, so now if I ask you, if osmosis is going to run across this membrane and the solvent's going to move, which way would it move? And what would these pictures look like in the end? Which way would it move? Would the solvent move this way, or would the solvent move this way? To the right or to the left? So write your answer down. Some of you cheated and scrolled to the next slide. The correct answer is that the solvent would actually move towards the left. okay, to dilute the solution with higher osmolarity until you get two solutions with equal osmolarity. That's the way osmosis works across the gradient. So now we have two solutions on either side of our membrane with equal osmolarity, and when you have equal osmolarity, we say the solutions are isotonic. That's the blank up here at the top. Same osmolarity, same number of particles per liter, and I don't have a poll question. Okay. All right. If you have questions on this, like I still don't understand how this works, or why did the solvent move from right to left or whatever, write those down, please, and email them to me, or what I actually prefer is that you come see me with them so I can discuss them with you in person and not via email. I hate discussing stuff in email. Sometimes I do it, but I prefer in person. All right, let's practice calculating osmosis, and we're almost done. Okay, when calculating osmolarity, ask yourself, how many particles or ions will this compound produce? And then you're going to multiply that by your molarity, okay? So let's say we have these compounds here, 0.5 molar of potassium chloride. This is going to break apart into potassium and chloride, which will be a negative. So I will get 2 particles, right? So I'm going to multiply this times my molarity and say, okay, I'll have 1 osmol. Or it would be 1 osmolarity. What about the next one? All I'm doing is I have 1 molar calcium chloride. Okay, calcium chloride is going to break apart into 1 calcium, right? I'm not looking at the charge. With equivalence, you would focus on that charge, right? But here, we don't care about the charge. We just care about how many particles. So I'd get 1 calcium and how many chlorides? I would get 2 chlorides. Total, 1 plus 2 is a total of 3 particles. We multiply the number of particles times our molarity, and that is 3 osmoles. Okay, can you do the last one ahead of me? Maybe pause the video and tell me what the osmolarity of 3 molar glucose solution would be. This is just going to give me 1 particle, right? Glucose is the particle. So obviously then times your molarity is just 3 osmoles. Because glucose is one of those biological molecules that does not break apart or dissociate into ions. Okay. So that is some example and some practice with calculating osmolarity from compounds. There's some more really good practice problems in the back of chapter 9 in the textbook. Okay, osmosis. So we have these pictures of some red blood cells here. Last 2 things on osmosis, this one, and then we're going to talk about one more slide. And it says we have red blood cells in isotonic solution, and then look, red blood cells in hypotonic solution and red blood cells in hypertonic solution. And obviously the blood cells look different in each solution. In the isotonic solution, they look like a normal red blood cell. They kind of look like a cushy, kind of like a donut, right? They have kind of like this dip in the middle here, which is the dark shaded region. And that's how red blood cells should look. But they look different in the hypotonic solution. They look swollen, okay, like kind of way more puffy than the ones on the left here. And why is that? I always have to change my color of my pen because red won't work on this picture. But I'm going to draw on this picture, and you should too. So for a hypotonic solution, what does that mean? That means the solution outside of these cells has a low solute concentration. And that means inside the cells we have high solute concentration. Okay. Now we have a gradient because we have a separation between our concentrations. They're not the same. So which way is the solvent? We have solvent in the blood cell and we have solvent outside the cell. And the extracellular fluid is what we call that. Which way is it going to move? Remember, it always moves from an area of low solute concentration towards an area of high solute concentration to try to dilute it. So simply doing its job via osmosis. Oh, red does not work here. It's going to, I think white actually works the best. It's going to rush in. All this extracellular fluid is going to rush into the cell, which is what causes the cells to swell. And if it rushes enough in, it would cause the cell to burst. Okay. And then why do the red blood cells look like this in hypertonic solution? These are shriveled. And then I'm going to write that they're swollen over here. So we had swollen red blood cells in hypotonic solution. Why are they shriveled in hypertonic solution? Well, how is the concentration difference working? If they're in hypertonic solution, what that means is the solution outside the cell has high solute concentration. And that means the area inside the cell has low solute concentration. So the solution is going to rush from low to high. So all of the solution is going to rush out of the cell trying to dilute the extracellular fluid. And when it does that, it leaves the red blood cell all shriveled like this, which is not good either, okay? So that's why it's important that our blood and our cells maintain proper equivalent levels, proper amounts of charge, proper amounts of solute in isotonic solution. Okay, again, any questions, write them down, and please come to me with your questions. Last slide here, and dialysis is just an example of what we're going to talk about, osmosis and oxygen transport, okay? So I've got two pictures. I've got your arterial veins and then your venous veins. Obviously, follow the white arrows. Our arterial end, these are veins coming from, they're freshly oxygenated blood, okay? Coming from the heart and lungs and being pumped throughout the rest of the body. So blood that is coming through these veins has a high concentration of oxygen. So I'm going to put an upward arrow, meaning a high concentration of oxygen. And it has just picked up oxygen from the lungs, and now it's going to be pumped by the heart through the rest of the body. Okay, so high concentration of oxygen, and it has a very low concentration of CO2 because we know at the lungs we exchange, CO2 is removed and exhaled, and then all the oxygen we're breathing in goes into our red blood cells, into our blood. Okay, so this is the conditions of our freshly oxygenated blood, and then that's going to be pumped throughout the body to our tiny blood vessels, which are known as capillaries. And this is where the exchange of oxygen and CO2 happens with our surrounding tissue and cells, okay? So I want you to notice a few things. Inside this capillary, you might notice these like purple circles. These are representing like red blood cells, okay? And then you might notice all these little dots right here, these little dots, which is, this capillary is a semi-permeable membrane. Okay, so through all these dots is where the exchange of things like oxygen and CO2 happens, okay? So we also have proteins. I want to acknowledge this. We have proteins down here in our blood, but proteins are really, really big, okay? And they cannot pass through these little teeny dots the way small molecules like oxygen and CO2 can. You can almost think of oxygen and CO2 as the solvent here. It's kind of weird to say. Not that they are the solvent, but they're small enough that they can pass through these capillary holes in our capillary like solvent can, okay? Now, larger things like the red blood cells themselves and the proteins cannot. They stay in the capillary, and then they move on through the venous veins and things back to our lungs, all right? But the oxygen and the small molecules like CO2 can travel in and out. They can passively move in and out. So their movement is going to be directed by a gradient. Okay, and you might notice, let's write this out, in our surrounding cells and tissues, these cells have been hard at work, and so they have used up any oxygen that was given to them, and they've created a lot of waste. So in the cells, we have a situation that looks like this: low oxygen content and high amounts of CO2. Whoops. Because they've been doing things, making things, That's what our cells do. They're machines that are constantly making proteins or replicating DNA, things like that. And in doing all these things, we make CO2 and we use oxygen. Okay, so these are the conditions on our cells. These cells need oxygen and they need to get rid of CO2 waste. Okay, now in the blood, what we said is we have high oxygen, low CO2. So you can see that oxygen is going to move from an area of high concentration in the blood. It's going to be forced and pushed out to an area of low concentration down here in these cells. CO2 is a high concentration in the cells, and it's going to be moved. Oh, I'm on eraser. It's going to be moved, follow these arrows into the blood where there's a low concentration of CO2. And that's the exchange we want to happen, right? We want to continuously deliver oxygen to the cells because they need it, low concentration of oxygen in the cells. So we're going to deliver from the blood to the cells all of our oxygen and other things, nutrients, other raw materials. And the CO2 is going to be pulled via gradient from the cells back into the capillaries, and then it's going to be delivered out to the lungs and exhaled. Okay? So that is how oxygen transport works. It's more detailed than that. It involves hemoglobin and things like that, but unless you're in a biochemistry class, we're not going to get into how hemoglobin works, which is really fascinating, but not a conversation for here. So last slide here. This is how dialysis works. People who have kidneys who can't filter out their blood for them, kidney failure, they will have their blood removed from their body via a dialysis pump. That pump will then take that blood, pump it into a dialysis solution. Okay, so in the blood, let me say here, in this blood we have high concentration of waste. And in the dialysis solution, which is the blue here, we have low, or I should say no waste. Okay, so that waste in our blood is going to be filtered out of the blood into the dialysis solution, and then we filter it back into the body. Okay. All right, that's it for solutions. That's all of Chapter 9. I have no idea how long this is, so if I went over time, I apologize. But we will recap on any of this at the beginning of class Thursday, and we will start Chapter 10 on Thursday as well.